Okay. In this chapter, or in this video, we're going to be looking at the oxidizing agents. This video should carry us through to the end of the chapter. Last time, you remember, we looked at reducing agents, and now we're going to be looking at the oxidizing agents. So we'll find that there are two main categories of the oxidizing agents that we'll be interested in. And those two main categories are reagents that contain an oxygen-oxygen bond. We'll look at those here in a minute. And those that contain a metal-oxygen bond. So some examples that include oxygen-oxygen bonds includes elemental oxygen, O2, ozone, which is also elemental oxygen, but a much more reactive version of oxygen, hydrogen peroxide, and then tert-butyl hydroperoxide, which is, again, that's just a peroxide. And then we also have peroxy acids, and we'll look at those quite a bit. The ones that we're going to be using the most in this chapter are going to be the peroxy acids and the ozone. Those will be the ones that show up in this chapter the most. So here are some peroxy acids. There's a generic form of a peroxy acid. You'll see a carboxylic acid would just have the carbonyl O and then H, but here this has an extra oxygen in it, and it makes this a pretty good oxidizing agent. Two commonly used peroxy acids that we'll see are peroxyacetic acid and metachloroperoxybenzoic acid. So these two are used. These have different solubilities, so that's a big reason why you'd pick one over the other, is solubility in your solvent. All right, oxidizing agents with metal oxygen bonds. All right, the most common oxidizing agents with the metal oxygen are either going to have chromium 6 oxide or manganese 7 oxide. And there are a couple of others that we'll look at here in a bit, but these two are the main ones. With the chromium 6, that includes CrO3, usually dissolved in sulfuric acid, aqueous sulfuric acid. Or you can have sodium or potassium dichromate, also usually dissolved with sulfuric acid, aqueous sulfuric acid. And then also pyridinium chlorochromate, which ends up being a more selective chromium 6 oxidizing agent. So you'll see here, this chromium has 6 bonds going to oxygen, giving it an oxidation state of +6. Now, I don't want you to think that that necessarily means it has a charge of +6 on the chromium. Its oxidation state is +6. Those are covalent bonds with oxygen, which is a little bit weird. We usually think of non-metal bonds as being ionic, but these are covalent bonds. But we'll find that that this is a chromium 6 oxidation state. The other one is pyridinium chlorochromate. Instead of having 6 bonds going to oxygen, we've got 5 bonds going to oxygen and 1 bond going to chlorine. That ends up making this have a -1 charge overall. So we need this pyridinium to balance out the charge, and so we call this PCC, pyridinium chlorochromate. Pyridinium chlorochromate. As I mentioned, this one is a little bit more selective, and I'll show you what I mean by that here in just a bit. Some other metal oxyanion oxidizing agents are going to include permanganate. I mentioned that one a minute ago, so potassium permanganate is commonly used. Potassium permanganate has a very distinctive purple color to it when you dissolve it in aqueous solution. So these are gradually increasing concentrations of potassium permanganate. Very widely used. It's relatively low toxicity compared to the chromium, but does have some toxicity issues. And some other ones that we'll find are osmium 8 oxide, or what's called osmium tetroxide. Here is the Lewis structure, and this actually has a tetrahedral molecular geometry to it. It's kind of interesting compound. So that's osmium tetroxide. And we'll find that silver oxide, Ag2O, is also a pretty good oxidizing agent in certain situations. All right. So now I want to kind of give you a preview of what's going to happen in the rest of this chapter, in the rest of chapter 12. We'll be talking about we'll talk about oxidizing alkenes, either to epoxides, diols, or cleaving it all the way to aldehydes and ketones. We can oxidize alkynes to carboxylic acids, and we can oxidize alcohols to form either aldehydes, ketones, or carboxylic acids. So pretty cool stuff that is coming up. So let's start with epoxidation. So we'll start with epoxidation. This is where we add a single oxygen to an alkene and form an epoxide. We typically will do this with a peroxy acid. This works quite well with peroxy acids. So here we've got an alkene with a peroxy acid. This is just a generic one. We form the epoxide plus carboxylic acid. So it's kind of like we take this oxygen here and we insert it in there and make single bonds going to the carbons and form the epoxides. This is a pretty clean reaction and pretty reliable. So here are a couple of examples. So ethylene with peroxyacetic acid gives us ethylene oxide and the acetic acid. And then here we've got a different alkene with the metachloroperoxybenzoic acid, and that gives us our epoxide plus the carboxylic acid as our product. So I'm going to show you the mechanism of this, and the mechanism isn't too bad, but I'm not going to make you reproduce the mechanism on the exam. What I want you to understand about the mechanism is that it is a concerted mechanism, and so it happens all in one single step. And furthermore, since it happens in one step, that means that the alkyl groups that are on the alkene do not have time to move around. So that means if you have a cis alkene, you'll have a cis epoxide as well. So if you have a cis alkene, you'll get a cis epoxide. If you have a trans alkene, you'll get a trans epoxide. We'll look at an example of that here in a little bit. So just in terms of how we would use epoxidation in the synthesis of a complicated compound, we can look at this natural product called Disparlure. It is a pheromone for moths, and it is of interest to scientists. They want to know how to synthesize it. So thinking retrosynthetically, so working backwards, here is the product that we want to make. We know that we can make epoxides using epoxidation with a peroxy acid, and so we know how to do that. Well, we know how to make cis alkenes from alkynes, and so we can do that with a reduction. Remember, the Lindlar catalyst will give us the cis alkenes, and then we can make alkynes. We can make alkynes by doing an SN2 reaction with these alkyl bromides. So by kind of thinking about it backwards first and then writing out the synthesis, we can come up with a way to make something like this. So I might ask you on a written out problem to synthesize an epoxide using this kind of synthesis method. So let me show you how that would work out. So the synthetic steps, the first step would be use the SN2 reaction 2 times to make an internal alkyne. So you'll start off with acetylene, deprotonate, do an SN2 reaction on an alkyl bromide, and that gives you this terminal alkyne. You'll do deprotonate, and then do an SN2 again on a different alkyl bromide, and that will give you this. That will give you that internal alkyne. Then we can do the syn addition of hydrogen with a Lindlar catalyst to give the cis alkene. So we can get the cis alkene by using that Lindlar catalyst, and that will give us that. And then finally, we can do epoxidation of that cis alkene to give us a cis epoxide. So using, again, here we're using MCPBA, and again, that's probably going to be because of solubility issues, why you wouldn't want to use the peroxyacetic acid. But MCPBA, you can epoxidize. Now you will get a pair of enantiomers, and it will be a racemic mixture of those. We'll find that one of them is the hormone that we're interested in, and the other one is biologically inactive. If it had been biologically active, we might have to separate it because that might actually have a very negative effect if we were using it for a particular application. Okay, so now that we know how to make epoxides, we want to look at how to get dihydroxyl groups, how to add two OHs across a carbon-carbon double bond. So dihydroxylation is the addition of two hydroxy groups to a double bond, and it forms a 1,2-diol, or as we like to call it, a glycol. So this is the process. So here we've got an alkene, and we can add the 1,2-diol. Now it turns out that there are two different ways that we can make this happen. One where we add the oxygens on both sides of this, on the same side of this carbon-carbon double bond, and one where we add them anti to each other. So if we add them anti, we'll end up adding, again, we'll have one OH on each carbon, but they will be added in an anti fashion. So they'll be opposite sides of our pi bond. And then here, if we add them syn, they will be same side. Now, if we have a simple compound like this, it wouldn't really matter which way we did it. But if we had a compound that was a cyclic alkene, that might make a big difference. And I'll show you an example of that coming up. So if we want, we can use epoxides to do the anti-dihydroxylation. All right, so first step is you would do an epoxidation using a peroxy acid. Again, it doesn't particularly matter which one you use. The MCPBA or the peroxyacetic acid would work, and we will get these trans 1,2-diols. So in the first step, we'll make the epoxide, and in the second step, we can cleave that epoxide using water with acid or water with base. It works on either one. If you're looking for the mechanism for that, you can go back to chapter 10, and it talks about cleaving epoxides. And both of these will work to give us a 1,2-diol that is trans. All right, so here is a more specific example with the MCPBA. We make the achiral epoxide. In this case, we're using the base, aqueous base. The base comes along, does an SN2 reaction. If it does the SN2 reaction on carbon A, then we'll get this, and we'll get our trans product. All right, and water is just there to protonate, so we'll get the trans 1,2-diol. And if it comes and reacts with carbon B, we'll get this, which is also a trans 1,2-diol. These are enantiomers of each other, and because all of this is achiral, this will be a racemic mixture. It's impossible to get one over the other if you start off with something that's achiral over here. If we want to do syn dihydroxylation, where we add the OHs on the same side, then we need to use something different. We can use potassium permanganate or the osmium-4 oxide. With potassium permanganate, we do it all in one pot. We don't have to do sequential reactions. So potassium permanganate, water, and hydroxide is a real nice reaction. It gives us the cis cyclohexane 1,2-diol. So that's very convenient. We can also use the osmium-8 oxide or the osmium tetroxide in one step, and then in a subsequent step, we can add the sodium bisulfite and water, and that will reduce it and get us back to this 1,2-diol. There are definitely advantages of each of these. The advantage of this is, one, potassium permanganate is pretty cheap, and this is all in one pot, so that's a big advantage. The advantage of this one is that it's not a strong base solution, so if you have something that's sensitive to bases, this one may be a good choice. The downside of this one with osmium is that osmium is kind of expensive. The price of osmium comes out to about $400 an ounce. With gold at about $1,800 an ounce, you can kind of get an idea. It's not quite as expensive as gold, but it's pretty expensive. All right, so with Syn dihydroxylation, each reagent adds the two oxygens in a Syn fashion. So we'll get the addition happening all at once. So we get two bonds, one oxygen going to one carbon, the other oxygen going to another carbon, and we form this. All right, so we form this as an intermediate. In the presence of aqueous base, it gets converted into the 1,2-diol all by itself. If you use the osmium, you'll get here, but then you have to add in a subsequent step the sodium bisulfite and water, and that will give us this. So we have to add an extra step in there. All right, so hydrolysis on this one occurs with just regular water and base, and this one, the hydrolysis occurs with the sodium bisulfite. We can get catalytic Syn dihydroxylation. As I mentioned a little bit earlier, osmium 8 oxide, the osmium tetroxide, is really expensive. And so rather than using a stoichiometric quantity of that, you can use a catalytic amount of the osmium tetroxide and a stoichiometric amount of the N-methylmorpholine N oxide, NMO. And this NMO is very effective at converting our osmium 6 product back into our osmium 8 product. I'm not going to show the mechanism for that, but you can just trust me, it does work, and we'll get the osmium 8, and that means that every osmium atom doesn't just do one reaction. It may do 10 or 100 or thousands of reactions. So it makes it a little bit more cost-effective to use this reagent in that case. So again, the NMO converts the osmium 6 back into osmium 8 oxide. All right, well, let's look at number 16 on the in-class assignment. Get that calculator out of the way. We're not going to be calculating anything. All right, so here, draw the products for each reaction. For this first reaction, well, this will do an epoxidation. So we'll end up with, that epoxide. And then when we do hydrolysis with the base, we will get a trans 1,2-diol. And I'll go ahead and put the other enantiomer as well. All right, didn't leave much room there, but we would get a 50-50 mixture of those two. If we use potassium permanganate and base plus a little water, we will end up getting the cis 1,2-diol. All right, so that gives us selectivity whether we want to make the trans or the cis. There might be some cases where we want the cis, and there'll be other cases where we want the trans, and so we need to know how to make both of those. All right, let's go back over to our presentation. So now we want to look at ozonolysis, and in ozonolysis we do oxidative cleavage of alkenes, And so we can convert an alkene. Into two carbonyl compounds. When we do the oxidative cleavage, we will break both the sigma and the pi bond that is in our double bond. So it's kind of like we come along with little molecular scissors, we cut that carbon-carbon double bond, and we replace each of those with an oxygen. We will get an aldehyde or a ketone depending on what R groups are here. If they're both carbons, we'll get a ketone. If one of them is a hydrogen, we will get an aldehyde. Here are a couple of examples. So with this, we oxidize that carbon-carbon double bond. Here we get a ketone. With this one, because it has a hydrogen, we'll end up getting an aldehyde there. On this one, we've got this methylene group here. So when we oxidize this one, of course, will be a ketone. And then here we're going to get formaldehyde because there's two hydrogens on that carbon. So that will remain. All right. You'll notice that I put here as a second step, I put zinc and water for one of these, and then dimethyl sulfide for the other one. And I'll explain why that is. If we don't put that in there, we're going to stop at something that's called an ozonide. So when the ozone adds to the pi bond, we get an unstable intermediate that's called a malozonide. And this malozonide will rearrange automatically, we don't have to do anything, to get the ozonide. And that ozonide is somewhat stable. And then, so we'll form that ozonide, and then we can reduce that ozonide to a ketone or aldehyde. We can produce that ketone or aldehyde, and then we'll either produce zinc hydroxide or dimethyl sulfoxide, DMSO, in the course of doing this, depending on which one of these reagents we choose to use. So you can use either one. They will both work. But without these as a second step, the reaction won't be complete. You'll stop at the ozonide. All right, we can do ozonolysis on cyclic alkenes as well. So when we do a diene or a polyene, we'll get oxidative cleavage of all the carbon-carbon double bonds. And if we happen to have a double bond that's part of a ring, then we will cleave that, and those will each become carbonyls. So again, you just have to look and see if there's two carbons attached to that particular carbon that's in the double bond, you'll get a ketone, and if there is a carbon and a hydrogen, you will get an aldehyde. In this case, there are two hydrogens, so you'll see over here we got formaldehyde. Again, you'll notice here we use the dimethyl sulfide as a reducing agent to convert that ozonide into our final products. All right, so now we want to look at oxidative cleavage of alkynes. So we'll look at the oxidative cleavage of alkynes. They also will undergo ozonolysis, but in this case, it's going to break not only a sigma and a pi bond, it'll break the other pi bond as well. We'll find that if we have internal alkynes, the internal alkynes are converted into carboxylic acids. So here we'll get a carboxylic acid. You'll notice with this that we just have to add water as a second step. We don't need the zinc or the dimethyl sulfide. So this one is a little bit easier to do. And here, if we have a terminal alkyne where we have a carbon hydrogen that's sp hybridized, that carbon is going to become carbon dioxide. And that, of course, is a gas, so it'll bubble right out of solution. All right, so let's look at number 49. Okay, so draw the products formed when in each oxidative cleavage, and so each oxidative cleavage. So the way I like to look at it is that we're going to sort of we'll just draw a line through there, and we're going to break that bond. And so that means that we're going to get O, CH3, hydrogen, so that'll be this part. And then this part, CH3, carbon, CH3. Oh, so that'll be acetone. So we'll get acetaldehyde and acetone would be our two products there. I'm not so concerned with what the byproducts are. I'm mostly concerned with what the organic products are. All right, here we're going to cleave this particular carbon-carbon double bond. And so when we do that, we're going to have 1, 2, 3, 4, 5, 6 carbons. This carbon will be in the chain, but so 7 carbons actually will be in the chain. So 1, 2, 3, 4, 5, 6, 7. And I'm going to number this. I'm going to number this so that we can see what's going on. So we'll call this carbon 1, 2, 3, 4, 5, 6, and that's just the methyl that's on the end. So this will be carbon 1, 2, 3, 4, 5, 6. All right, so carbon 1 that was in here, that will become a ketone, and then carbon 6, because it has a hydrogen on it, it will become an aldehyde. And that will be your product for that one. So I definitely encourage you to count the carbons out and make sure that you have enough in there when you're doing this. When we do ozonolysis of this, here we have an internal alkyne. So we're going to cleave this. These carbons will become carboxylic acids. And since it's symmetrical, we're going to end up with 2 of these. So we'll get carboxylic acid, and I'll just put 2 of those. Okay. On this one, we'll oxidate it. We'll get the oxidative cleavage here. So we'll cut that, and we will end up with cyclohexanone and acetone. All right. So this part becomes the acetone, and then this part becomes the cyclohexanone. On this one, you'll see that we've got a terminal alkyne, which means this part here will become a carboxylic acid, and the part on the end will simply become carbon dioxide. So 1, 2, 3. All right, so that's this carbon. There's that carbon, that carboxylic acid. And then I'll put CO2 will be our other product. All right, so going back to our oxidative cleavage of the alkynes. All right, so now we want to look at oxidation of alcohols. And when we're oxidizing alcohols, we're going to increase the number of oxygen bonds going to that carbon that are in the alcohols. And so the results are that we can oxidize alcohols to carbonyl compounds. All right. And each type of alcohol will give a different product, and the reagent will help us to determine what product we're going to get. So if we have a primary alcohol, when we oxidize it, we'll either get an aldehyde or a carboxylic acid. Again, we can choose which one it is based on which reagent we choose. For a secondary alcohol, there's just not much choice there. We'll oxidize that to form a ketone when we do that oxidation. And then finally, with tertiary alcohols, if we attempt to oxidize it, we'll get no reaction. The reason for this is that you need to have a hydrogen on the carbon. So here's a hydrogen. This one has 2 hydrogens. You need to have at least 1 hydrogen on that carbon in order for this oxidation to occur. The only other real choice we have for oxidation would just be to like burn it, catch it on fire. But that's not what we're looking to do here. We're looking to make aldehydes, ketones, or carboxylic acids. All right, so let's look at our chromium 6 oxidizing agents. We talked about them a little bit earlier. And so we need to use something that is a chromium 6 oxidizing agent. And they end up getting reduced to chromium 3 products. So the most common choices are going to be chromium 6 oxide, so CrO3, sodium dichromate, or potassium dichromate. Those are good choices. And then we usually use them in aqueous acid solution, so we'll have sulfuric acid and water. If you just use this, the CrO3 plus sulfuric acid and water, you often call that chromic acid solution. So here is the chromium 6 oxide. One thing I want to point out about that chromium 6, its oxidation state is +6, but that doesn't mean that its charge is +6. It turns out that those chromium oxygen bonds are covalent bonds and not ionic bonds. Typically, we think of metal nonmetals as having ionic bonds, but it turns out that these are covalent bonds, so we don't have to completely transfer the electrons, so we don't have a +6 charge on the chromium. There is a positive charge, but it's definitely not a +6 charge. You'll notice that there are 6 bonds going to oxygen. Here we've got another one that's called pyridinium chlorochromate. The pyridinium chlorochromate is a milder oxidizing agent. It is a +6 oxidation state, but you'll notice it has 5 bonds going to oxygen and 1 bond going to chlorine. Well, that 1 chlorine makes this a less potent oxidizing agent, and so it doesn't oxidize other things as easily as the chromium 6 oxide. The pyridinium just acts as a charge balance, and so we get this ionic compound, and then this is our oxidizing agent right here, is that chlorochromate. We usually just call this PCC for short, and if I'm asking you to solve a problem, you can write PCC on there. Okay, so let's look at secondary alcohols first. With a secondary alcohol, we can use any of our chromium 6 oxidizing agents to oxidize our secondary alcohols into ketones. So here we've got isopropanol, which is just rubbing alcohol. And if we use the potassium dichromate, sulfuric acid, and water, we can oxidize that and form this. So we can form this, which is acetone. If we use the pyridinium chlorochromate, we'll get pretty much the same result. So there are reasons. The pyridinium chlorochromate is a little bit more effort. This is like practically free, and this is not. So there are reasons why you might want to use the pyridinium chlorochromate. You don't have to have sulfuric acid in there, and if you happen to have some other functional group on your compound that's sensitive to acid, then PCC might be the optimal choice. So when we're oxidizing a secondary alcohol using a chromium 6 oxidizing agent, this is the mechanism. I am not going to make you reproduce this mechanism on the test. What I want you to know about this mechanism, though, is that the oxygen does react with the chromium. Okay, we'll do a deprotonation of this hydrogen, so we have this chromium oxygen bond there, and then this is important. We have a hydrogen that is on the carbon that originally had the OH group. Without that hydrogen, we can't do the rest of the oxidation. So this is why we can't do tertiary alcohols, because we don't have that hydrogen on there with a tertiary alcohol. But here with a secondary, we can deprotonate that, make the ketone, and then we'll get this chromium. This is actually a chromium 4. That chromium 4 will in turn get reduced to chromium 3 a little bit later. If we have primary alcohols, on the other hand, primary alcohols are oxidized to either aldehydes or carboxylic acids, depending on which reagent you choose. If you choose the milder pyridinium chlorochromate, the PCC, you can oxidize it simply to the aldehyde. If you use the sledgehammer oxidizing agent, the either dichromate or the chromic acid, which is the CrO3 and sulfuric acid, any of these, you're going to oxidize all the way to the carboxylic acid. And what happens here is that this oxidizes twice. So that the chromium 6 will oxidize this twice to give you the carboxylic acid. It will, in the intermediate, give you the aldehyde, but then that aldehyde in turn will get oxidized to form the carboxylic acid. All right, so here we've got a primary alcohol, and in our first step, we will oxidize it and we will form an aldehyde. The second step is a hydrate. We'll talk about that in a later chapter. And then there's another couple of steps here in which we can convert that hydrate into the chromate ester and in turn into a carboxylic acid. Right now, what I want you to understand is that if you have a primary alcohol and you use the strong oxidizing agent, which is CrO3 plus sulfuric acid, or dichromate plus sulfuric acid, I'm going to go back a page, so any of these, then you're going to oxidize it twice and get carboxylic acid. If, on the other hand, you use the PCC, you're only going to oxidize it once to give you the aldehyde. The PCC will not affect the aldehyde. If you have the aldehyde in the presence of one of these chromium oxidizing agents, you will oxidize it to the carboxylic acid. All right, so kind of an interesting trick that people figured out a long time ago to do was to use this chromium system to measure the blood alcohol content. So you could create a very simple device that has a chemical in there and get a pretty good approximation of somebody's blood alcohol content. And so this used to be used for like roadside tests to determine if somebody was impaired. Now, they have much more sophisticated electronic equipment now, and so they usually don't use this system anymore, but this is still kind of cool as a way to do this. Now, of course, when people drink alcohol, they're drinking ethanol, which is a primary alcohol, and that primary alcohol will get oxidized. Well, the thing that oxidizes it is chromium 6 oxide. It has a red-orange color to it. When it does oxidize the alcohol, the chromium 6 will get converted into chromium 3, and the chromium 3 has a green color to it. So that chromium will get converted from orange to green, and that's pretty easy to see. When you're looking at one of the tests. So the way that they make this work, so whenever somebody has alcohol in their system, the higher the concentration of the alcohol in their system, the higher the concentration of the alcohol in their breath. This is why if somebody's been drinking and you smell their breath, you can smell the alcohol on them, as can the police officers, which is why I'm going to take this moment to say, please do not drink and drive. All right. So, but people can smell that because there's alcohol physically in your breath. Well, when you blow that air out and some of that alcohol goes through one of these devices, the alcohol will get converted into acetic acid. And when that happens, it will convert the chromium 6 into chromium 3. It'll go from being orange to green. All right, so you breathe it through there, and depending on how far the green goes, you can determine how much alcohol is in the system. Now, they also have systems that tell you, are you over the limit or under the limit, and that's all it tells you. And so there you breathe through the tube, and it can, if you see the green, then that means that there is enough alcohol that it has, that they are over the limit. So again, this type of test has fallen out of favor in favor of things that are a little bit more reliable. This tends to have some variability to it, and you probably, as a district attorney, don't want to lock somebody up on something that's like using this kind of test. Instead, they can use electronic equipment, and if they're really in doubt, they can get a blood test And blood tests are much more precise when making blood alcohol measurements. I looked online to see if I could find these, and these are really rare now. People just don't use these as often as they used to. You can find some on eBay and on Amazon, but they're not quite the same as what you see here. All right. Anyway, the more alcohol in the breath, the more green is produced, and then you get a pretty good idea of how much alcohol somebody has in their system. Pretty cool technology. Again, it's all been replaced by stuff that's a little bit more accurate, but pretty neat. All right, we want to look at some green chemistry, and the green chemistry is things that are environmentally benign to do synthesis. What I have shown you is I've shown you some things that use chromium. Well, chromium turns out to be a pretty toxic metal. It's a heavy metal that you don't want in your waste stream. And so to eliminate it from your waste stream, they've come up with some green chemistry things that they can do. So you know, some of these use some toxic reagents like the osmium and the ozone. Those are toxic. Not to mention the osmium's quite expensive. And then the corrosive reagents like sulfuric acid, that is problematic. And then also produce some carcinogenic byproducts. Chromium-3 is a carcinogen and a heavy metal, something that you don't want. Like I said, you don't want in your waste stream. So one of the techniques is that they still use chromium, but they absorb it onto the surface of a polymer called Amberlyst A26, and it's a resin. And when you absorb that chromium onto there, you can avoid using a strong acid, and you get a chromium-3 byproduct that stays with the polymer, stays with the resin. And so you can simply filter it out. So your reagent is stuck on the surface of that polymer. And so there is a complex hydrocarbon network with a cationic ammonium ion appendages that serve as counter ions to our chromium agent, this is the bichromate or bichromate. So here we've got we've got our polymer with our oxidizing agent. If you heat that polymer reagent in the presence of an alcohol, you can get oxidation. You can get oxidation to an aldehyde. You'll notice that this is a milder oxidizing agent than just chromium-6. It acts more like PCC, but you do have to heat it up to do this. Your polymer keeps the chromium-3 on it, which means you can filter it off, and it's possible to regenerate that chromium, go back to chromium-6, so you can reuse this, which that's pretty cool. So here's an example. We've got the HCrO4 with a -1 charge absorbed onto the Amberlyst A26 resin. We can oxidize our secondary alcohol, and we've got our ketone present. There is another oxidizing agent that is considered green, and that is potassium peroxymonosulfate, so KHSO5, which that's a lot of oxygens. And the reason that we have that extra oxygen is that there is an oxygen-oxygen bond present. So it is sort of a sulfur derivative. It's a sulfate derivative of hydrogen peroxide, usually in the form of a salt. So you have potassium bisulfate, potassium sulfate, and then potassium peroxymonosulfate, all present at once, and that's called Oxone. And it can oxidize a whole bunch of groups without having to have a heavy metal like chromium or manganese, and so your byproducts are much safer. And then here we've got some solvents. This is a polar aprotic solvent, which is acetonitrile water, and then we have an ionic compound that makes it all possible. I'm not showing the mechanism for this. I'm just saying that if you have a primary alcohol, it will convert it into an aldehyde, and if you have a secondary alcohol, Oxone will convert it into a ketone. So it acts like PCC and the Amberlyst resins when oxidized. Okay, so let's look at number 50 on our in-class assignment here. So here we are oxidizing. We're oxidizing this particular alcohol. Or here we've got we have a secondary alcohol and a primary alcohol. 1, 2, 3, 4, 5 carbons. So I'm going to draw the 5 carbons. With PCC, it'll oxidize the secondary carbon to a ketone, and our secondary alcohol to a ketone, and our primary alcohol will get converted into an aldehyde. All right. If we use the chromic acid solution, so CrO3 with sulfuric acid and water, it'll do the same thing to the secondary alcohol. So 1, 2, 3, 4, 5. So we'll still convert that secondary alcohol into a ketone, but our primary alcohol will get converted into a carboxylic acid. All right, on this one, I've got 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. And then here, Oxone will convert our secondary alcohol into a ketone. And Oxone with an aldehyde won't do anything to our aldehyde, so it will remain an aldehyde. With chromic acid, it will oxidize. All right, let's scoot that up a little bit. All right, with the chromic acid, it will oxidize the secondary alcohol into a ketone, but then it will oxidize this aldehyde into a carboxylic acid. And that's an important concept why I picked this particular molecule. All right, it is possible to oxidize using other reagents. There is one that's naturally occurring that will convert alcohols into aldehydes, and that is the NAD. All right, nicotinamide adenine dinucleotide, which is this big old thing, and you'll see that you can convert a primary alcohol. Or this is a secondary alcohol. It'll convert the secondary alcohol into a ketone. So you will get a carbonyl containing compound. It works in a similar fashion. I'm not going to get into the details of it other than to say, hey, that's kind of cool. It's something you don't have to have chromium in your body in order to oxidize something. So that's a good thing. All right, our last topic in Chapter 12 is looking at enantioselective epoxidation. So enantioselective epoxidation. And so to preface this, I want to say that if you have an achiral starting material, and achiral reagents, meaning they are not chiral, then you will either produce an achiral product or a racemic mixture of two enantiomers. It's impossible to take an achiral starting material and an achiral reagent and produce just one of the enantiomers. In order to take your achiral starting material and convert it into just one enantiomer, you have to do one of two things. Either one, you have to use a chiral reagent, or two, you have to separate your products at the end. All right. So achiral starting materials cannot produce just one enantiomer unless it's combined with a chiral reagent that happens to be enantioselective. And not all chiral reagents are enantioselective. Some are, and the one that we're going to look at is called the Sharpless Epoxidation. So named after a chemist named Barry Sharpless, who, by the way, won a Nobel Prize for his work on this. In the Sharpless epoxidation, the double bonds of an allylic alcohol can be converted into an epoxide. This is an enantioselective reaction, which means that we get one enantiomer over another enantiomer. And so we'll say that a reaction that converts an achiral starting material into one enantiomer is called an asymmetric reaction. And again, the only way you can do this is if you have chiral reagents. And so our Sharpless reagents are chiral. All right, so here is an allylic alcohol. It is achiral. Here's our Sharpless reagents, and I'll talk about these in more detail here in a minute. We do have this epoxide, and then the tartrate is the chiral part. And then if you use one of the enantiomers of the tartrate, the diethyl tartrate, you will get oxidation from above this. So you'll get oxidation on the top of this. And if you use the other one, you'll get oxidation on the bottom. So I'm going to show you an example of how this works. All right. The three components that you use are tert-butyl hydroperoxide. So this is a tert-butyl group with OOH. This is not a carboxylic acid. This is a peroxide. So this carbon already has 3 carbons attached, and then oxygen, oxygen, hydrogen. A titanium catalyst. So the titanium for isopropoxide, which is this thing. And that's it. All right, hold on. All right, through the magic of pausing, I fixed that little typo. So Ti, that's a titanium catalyst. And then diethyl tartrate is our chiral sort of adjunct in this whole thing. All right, so there are 2 different chiral diethyl tartrate isomers, and I'll show you the pictures of these. These are the 2 enantiomers of the diethyl tartrate. The plus indicates that it rotates plane polarized light clockwise. The minus indicates that it rotates the plane polarized light counterclockwise. And which one of these you add to your reaction will determine what product you get. So let me show you how that works. All right, so up here we've got our allylic alcohol, which means we have an OH that's on the carbon that is adjacent to our carbon-carbon double bond. You'll notice here we're using the plus DET, and that plus DET, you'll see that we get one enantiomer predominantly over the other. Here the epoxidation happens on the back side, on the bottom. All right, happens from below. And you'll see 97.5 to 2.5. That's an enantiomeric excess greater or equal to 95%. That's very, very good. All right, if we use a similar one here, we use the minus DET, we will get this as our major product instead. If we use minus DET, we would have gotten this one as our major product. So, so what we need to do is we need to remember which one gives us which product. All right, so determining which Sharpless epoxidation product you're going to get, it's best to draw the allylic alcohol in a plane, and I will show you how that works. With the OH in the upper right corner, so you can imagine it in a corner. I don't particularly like this drawing. I'm going to show you a different drawing here in a moment. But in the upper right-hand corner, you have the CH2OH, all right? And the minus DET will add the epoxide on the top side of this, and the plus DET will add it on the bottom side of that. All right. So now let's look at 41, and 41 has some problems from the whole chapter. So this one is kind of kind of good. So here. All right. So here we have an allylic alcohol. And we want to see what happens when we do each of these reactions. All right, so we'll start with A. So A is hydrogenation. We're just going to add hydrogen across that. So 1, 4, 5. The OH will stay exactly like it is. but we will hydrogenate it and turn it into just a regular alcohol instead of an allylic alcohol. Okay. If we do B, all right, so B, MCPBA is it's a peroxy acid. It will oxidize this and form a peroxide. And that peroxide is going to be we're going to get a mixture of products because it can oxidize both below and above. So we'll get one. All right, so here we'll get O like that. And we will also get that epoxide where the oxygen is facing down. So we will get a 50-50 mixture. It will not be enantioselective, right? PCC is a mild oxidizing agent. It converts primary alcohols into aldehydes. So C is going to give us it will not affect that carbon-carbon double bond, but we will get an aldehyde. So that's with the PCC. With chromic acid, so the CrO3H2SO4. So we'll do D. All right, that part of the compound will remain the same, but here, this will be a carboxylic acid instead of an aldehyde. So it'll oxidize that alcohol all the way to the carboxylic acid. All right, with E, this is the Sharpless Epoxidation. And with the plus, it's from the backside. So we're going to get this. All right, so we will get that. And for F, it's the minus, so it'll be from the front side. All right, and we will get that. And then finally, with G, all right, we'll go ahead and do each of these. So on G, all right, so step 1, which is PBr3, that will convert the alcohol into an alkyl halide. So we'll go ahead and draw that. To a bromide. And then the lithium aluminum hydride, all right, so the LiAlH4, so 2, and then 3 is just with the water. That will convert it into an alkane. And so you'll simply get that. So H2O, alkane. So this is the reduction on part G. That's the reduction that we saw in earlier on in the chapter. All right, we're going to go back to our screen and I'll show you my favorite page of every chapter, which is the last page. That means we are done. So that is the end of chapter 12.